Hello, dear students. Welcome to Biology Decrypted, and the series which is going on is Biochemistry Decrypted, and I welcome you to lecture 1 of this series in pure English. That is Chemistry Fundamentals Part 1. Chemistry Fundamentals, as you know, it's very important because the subject you are studying is biochemistry, and so chemistry becomes the very base of this particular subject. Now, to start with, we will recapitulate atomic structure. Well, I won't start from class 9th or class 11th atomic structure. Like, I won't be discussing Rutherford's model or say Bohr's model or say Thomson's plum pudding model. I won't be discussing all of that. What I will start with is the concept of quantum numbers. Now, you might have heard about it, you might not. So the topic is quantum numbers. Well, these quantum numbers are very important because later on they will help you to decide what is the electronic configuration of any atom or ion or molecule. Fine. So electronic configuration can be written for atoms, for ions as well as molecules, because if you would have heard about MOT or molecular orbital theory, there we actually assign the molecular electronic configurations for various diatomic molecules. Now, first we'll discuss this about atoms. Okay, let's take an example of atom. An atom, as you know by definition, it is electrically neutral. And this phenomenon is called as electroneutrality. Is that fine? Now, talking about this electroneutrality, what does this mean? This simply means that the number and magnitude of charges is equal. Number and magnitude of charges is actually equal. Now, what are these charges? Well, it's very obvious. Positive charge and negative charge. Now, which are the positively charged subatomic particles? Very simple. Protons. And what about the negatively charged particles? Well, electrons. Fine. So protons, electrons, we now know these are the charged particles. And in order to maintain this electroneutrality, it is very important that the number of these subatomic particles remain the same. So for a neutral atom, there will be equal number of protons and electrons. So number of protons, well, I'll denote protons as P plus and electrons as E minus throughout, so that I don't have to write protons and electrons all the time. So number of protons will be equal to number of electrons. And this will be the case only in case of atoms. And by definition, atoms are electrically neutral. So I hope this is fine. Now, see one important thing. You can actually imagine this in the form of a tug of war. How? How is it related to a tug of war? Well, if you see, in this atom, there is a nucleus. This nucleus is responsible for all the positive charge the atom has. And it is surrounded by these shells where you find the electrons revolving. Here in the nucleus, you find protons and neutrons. So let's summarize. Protons, neutrons, these are present in the nucleus. Electrons are actually revolving around this. So these are actually revolving around this. And the number of protons will be equal to the number of electrons in case of electrically neutral atom. So if you say, I am striking out an electron from an atom. Let's say we are taking an example of sodium atom, Na. Fine. So this is our sodium atom. And this sodium atom has 11 protons. Okay, 11 protons. How do we denote it? Let's see how do we denote it first. If I have sodium atom here, I am writing 11 here and I am writing 23 here. What does this mean? And this is the way how most of the elements, most of the atoms are represented in this way. So basically, this is a general way of representation. If I write X here and I write A here and Z here, what do these symbols stand for? A stands for mass number and Z stands for atomic number. Z stands for atomic number. Now, if you see, this mass number actually represents the number of protons plus the number of neutrons. And this atomic number simply represents the number of protons. So number of protons is Z, that is atomic number, and number of protons plus number of neutrons gives you the mass number. So here you can easily say that this is the mass number and this is the atomic number. If I ask you, find out the number of neutrons in this case, it's very simple. What would you do? You can simply find out number of neutrons by subtracting Z from A, which means A minus Z will give you the number of neutrons, because Z is the number of protons and A, that is the mass number, is the number of protons plus the number of neutrons. So basically you will get the number of neutrons from here. If you check it for sodium, you will get 23 minus 11, that is 12. So there will be 12 number of neutrons. Now let's fill the data sheet. Number of protons will be 11. Number of neutrons will be 12, and number of electrons, since this atom is electrically neutral, I am not talking about any ion here, I am talking specifically about sodium atom. Therefore, the number of electrons will be the same as the number of protons, that is 11 again. But now comes the surprise. What if I strike out an electron from the sodium atom? What if I throw one electron away? What will happen? Now the tug of war was balanced. There were equal number of electrons and protons, 11 protons for 11 electrons. What if I strike out one electron away? Now in this case, see, we won't look at neutrons, because neutrons do not contribute anything to the charge. They do contribute to the mass, but not to the charge. So number of protons in this case will remain the same, because it is inside the nucleus and we are not disturbing the nucleus here. So the number of protons remain 11. But when we talk about the number of electrons, what happens is the number of electrons reduces. Now you see that the net dominant charge here is +1 because one electron went away and this extra proton is dominating now. So this is responsible for a +1 charge, and now it is no more called an atom because it is not electrically neutral anymore. It has charge. It is a charged species and therefore it is called as cation. So generally it is called as an ion, and specifically we call it cation because of its positive charge. So this is basically sodium ion or sodium cation. This is what I showed you. Fine. So now we'll move forward. This is what we had seen. Next we saw the formation of sodium ion. Now let's see the formation of an anion. What is an anion? Anion is obviously negatively charged. And now let's take an example of chlorine. Chlorine with an atomic number of 17. You can easily understand that Z is 17 here. So number of protons will be 17. And since this is still electrically neutral, the number of electrons will be 17 as well. And therefore this whole atom has a net charge of 0. Now, what will happen if I add an electron? If I add an electron to this chlorine atom, what will happen is Cl- will be formed. Because in this new case, what will happen is the number of protons will be 17, but there will be one extra electron entering, and total number of electrons will be 18. Therefore, there will be an extra negative charge and a net charge of -1. And therefore, chlorine will get converted into chloride. So this is chloride ion, or simply we can call it an anion because of its net negative charge. So this is the concept of formation of cation and anion, and we saw this through an example of sodium and chlorine, sodium atom formation as well as chloride atom chloride ion formation. Now if we take an example of sodium again, so here is our sodium. Now it has 11 atomic number, and now if we try to arrange the electronic configuration from class 9, just try to remember K, L, M, N ... These many shells were there. I hope you remember. This is how you had the nucleus. There was the first shell, that is K, L, M, N. This is how you had studied about Bohr's atomic model, right? So this was K, L, M, N, and infinitely increasing. See, if we try to denote a number to each of these shells, for example, if I say for K I am writing n is equal to 1. So this is the first shell. Then there will be n is equal to 2, n is equal to 3, n is equal to 4, and so on. And so on. Now, talking about this one, there will be 2 electrons in the first shell. So the maximum number of electrons will be 2 here. In the next one, there will be a capacity to accommodate 8 electrons. So there will be 8 electrons here. Then in the next one, you can have 1 electron. See, you just have to fill the electrons here. 2, 8, 1. Total, you add them, you'll get it as 11. Now, what is this? I was talking about quantum numbers, right? Here comes the first quantum number. So basically, this n is the first quantum number, and this is called as principal. This is called as principal quantum number. Principal quantum number, or small n. Now, this principal quantum number, as you know, it simply denotes n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, tending to n is equal to infinity. Up to n is equal to infinity, it can go. So this is the principal quantum number. What you can say is, from this, basically quantum numbers, what they do is they give you the address of electrons. So as I told you, we'll start with quantum numbers. Quantum numbers tell you the address of electrons. So where the electron is, for example, if you talk about an atom, in this particular atom, where the electron is, which shell am I talking about? Okay, now in this shell, we'll talk about the subshells. We'll talk about the subshells, and we'll talk about the orbitals. We'll talk about the orientation of the electron in the orbitals, and this is how we'll get all the information concerned about each and every electron in a particular atom. And that's how we write the electronic configuration. That's how we get to know the position of a particular element or an atom in the periodic table. That's why this information is of so much importance. So now, coming to principal quantum number. This is how we decided the principal quantum number. It's very simple. Let's move on to the next quantum number. So this is the first quantum number. Now we'll move on to the second most important quantum number. That is the azimuthal quantum number. Azimuthal quantum number, also denoted by small l. Now, remember this. L starts from 0 and it ranges to n minus 1. So, what does this mean? This simply means that it cannot be equal to n. Simple meaning is L can never be equal to n. It is always 1 less than n. Whatever would be the maximum value of n, L will assume a value that is 1 less than that maximum value. See, if we have n is equal to 1, for n is equal to 1, we'll have L as 0 and only as 0, because it cannot be 1. L cannot be 1 for n is equal to 1, right? It is always 1 less than the value of n. Okay, that's fine. Let's move to n is equal to 2. Now for this second orbit, we see L can have a value of 0. Obviously, it can have a value of 0. And it can also have a value of 1. L can be equal to 1 as well. Now, for n is equal to 3, we'll have the value of L as 0. L can be 1 and L can also be 2. Similarly, for n is equal to 4, L can be 0, L can be 1, L can be 2, L can be 3 as well. And so on. This goes on. This goes on. Now, let's talk about an important thing. When L is 0, whenever L is 0, we call it as S. Whenever L is 1, it is P. Whenever L is 2, it is D. Whenever L is 3, it is F. So did you get it? These are the subshells. And whenever the electron enters these subshells, in the broader picture, you talk about S block, P block, D block, and F block elements in the periodic table. So basically, everything arises from these quantum numbers, and then comes electronic configuration, and finally you get the position of particular elements in the periodic table. You also get to know the reason behind calling these specific blocks in the periodic table. Fine. So yes, this is how it arises. So now what we can say is, if the N value is 1, L value is 0, simply this denotes 1s. Fine, it is 1s. Earlier we were talking about just shell number 1, but now we are talking about the subshells, that is 1s. Now for L is equal to 0 but N is equal to 2, for this you see that this stands for 2s and this will stand for 2p. Now if we talk about N is equal to 3, L is equal to 0, so this is 3s. Similarly, this is 3p, and similarly this is 3d. Now I hope you get the reason why 1p is not possible, why 1d is not possible. Similarly, why 2d is not possible, 3f is not possible. These are the exact reasons, because L cannot assume a value equal to N, and there's no question that it cannot, like, it's very obvious that it cannot assume a value greater than N as well. It will always be less than N, 1 less than N. Fine. So now for N is equal to 4 and L is equal to 0, 4s. This stands for 4p, 4d, and 4f. 4f. Just a moment. Yes, this is 4f. So this is how we could write all the subshells that are possible. Now, in these subshells, we'll be seeing the orbitals or the rooms in which the electrons are residing. So what we'll do is, now we'll move on to the third quantum number. So when we talk about the third quantum number, yes, so the third quantum number is the magnetic quantum number. Now, whenever we'll talk about the magnetic quantum number, or we denote it as ML, as you can see, it depends on L, and basically it is the range of L. What does it mean, range of L? Simply it means plus minus L. Whatever the value of L is, it will be a range of minus L to plus L, minus L to plus L, which includes 0 of course. Now if I talk about L is equal to 0, because ML is depending on this value of L, that is your azimuthal quantum number. So what we'll see here is, for L is equal to 0, ML will be 0, because obviously 0 doesn't have a range, it is 0 simply. Now if I talk about L is equal to 1, for L is equal to 1, you will see that ML has a range of 1, that is from minus 1 to plus 1 through 0, right? It has 3 values, minus 1, 0, plus 1, and basically this denotes, if you try to draw it in the form of boxes, This is basically called as the box orbital diagram. So what I'm showing here is box orbital diagrams. And this is an example of box orbital diagram. For ml is equal to 0, you can have one box. This is just one room that it is signifying. Here there are three possible arrangements, three possible rooms. Now for L is equal to 2, you will have ml as -2, -1, 0, +1, +2. And here you will be creating these 5 boxes. Box orbital diagrams. So the actual orbitals will look slightly different. I'll be minimizing myself and I'll be showing these diagrams to you so that you can appreciate the shapes of the particular orbitals. So what we see here is for s orbital, the probability is equal in all directions. If you see, it is spherical from all sides. So let's draw it this way. If you try to denote the 3 mutually perpendicular axes, that is the x-axis, y-axis and z-axis, you see that the s orbital is spherical and it is arranged in this way. Now if you talk about the p orbitals, in case of p orbitals, it is not arranged in a way similar to the s orbitals. What happens here is one p orbital will be along the x-axis, one will be along the y-axis, and one will be along the z-axis. There are 3 p orbitals. See, here there was only one s orbital. Only one s orbital was there. Yes, the size can vary. The size can vary. It can be 1s, it can be 2s, 3s, 4s. The size can increase, but yes, it will have just one orbital. For p, you see that there is one px orbital, there is a py orbital, there is a pz orbital. So there are 3 such orbitals. Size can obviously increase if it is 1s, 2s, 3s, 4s, or 1p, 2p, 3p, 4p. So as you increase the value of principal quantum number, obviously the size of the orbitals will increase. Now let's talk about this. So here we'll talk about px, py, pz. That is their orientation along the particular axis, and this is how you see the orientation. You get information about the orientation from the magnetic quantum number. Now if we talk about the d orbitals, as you can see here, the different d orbitals are dxy, dyz, dxz, or dzx, you can say, then dx square, y square, dz square. These are the d orbitals and these are degenerate. Degenerate means they are equivalent in terms of energy. So what you see here is there are 5 d orbitals possible. There were 3 p orbitals possible, 1 s orbital possible, and now you can predict the same thing for L is equal to 3. That is when you talk about s, p, d, and finally here for L is equal to 3, f orbitals. For f orbitals, the ml values will range from -3, -2, -1, 0, +1, +2, and +3. These will be all the 7 boxes possible. So these are the 7 boxes that are possible, and the shapes of the orbitals are too complicated. These look like flowers, flower petals. So yes, we don't generally talk about f orbitals in our discussions. What we'll talk about is the d orbitals. See, I'll just generally draw this. For d orbitals, what we do is, if it is d xy, yz, zx, in all these cases it is present between the axes like this. And as you can see, for p orbital, the shape is here, this shape was spherical. For p orbital, it is dumbbell. Yes, the dumbbells found in the gyms. And this shape is called double dumbbell. Double dumbbell shape for d orbitals. So this is for dxy, dyz, dzx. If I talk about this, is dx square y square, and this is the shape for dz square. This is the shape for dz square. So this is the overall picture of the different orbitals, that is s orbital, p orbital, d orbital, and we didn't talk about the shape of the f orbitals because it's not necessary. What's important is for s, p, and d. Now we have seen, let's just recapitulate. We saw the shell in which the electron was residing. We zoomed further. We found out the particular subshell in which the electron was residing. Now we looked at the orientation in that subshell and we found the various orbitals in which the electrons are staying. Finally, we'll see where the electron is and how the electron is residing there. So coming to the fourth and the final quantum number, that is spin quantum number. Spin quantum number. This is also denoted as ms or simply small s. Fine. So now, whenever there is a box orbital diagram like this, electrons will be present in this way. Either it is empty or it is half filled. So this is an example of s orbital. So this s orbital, this ns orbital is fully filled. This is fully filled. Now if I talk about this s orbital, so this can be written as ns2, this can be written as ns1. This is half filled. And similarly, if you see here, this is empty. This particular orbital is empty. This is an empty orbital. Now, if you talk about p orbitals, for p orbitals, this was earlier it was empty. Now I have started filling the electrons. The rule for filling the electrons is very important. This is called as Hund's rule of maximum multiplicity, maximum spin multiplicity. So the meaning is the spin should be maximum first while filling. You have to keep it maximum. You cannot do pairing simultaneously. Once all the orbitals are half filled, only after that you will start pairing. So the simple rule is, first you fill it half and then you fill it full, not the other way around. You should not pair it before filling it half. So this is how you fill the p orbitals, and it is in sequence. It's very simple: p1, p2, p3, p4, p5, p6, like this. For d also is the same. Maximum electrons that can be accommodated in 5 boxes will be 10, because there will be 2 electrons accommodated in each orbital, in each box. So now talking about the spin quantum number, as we saw, the electrons are oriented in this manner. Now this is a system in which it is paired. There is one electron which is denoted in this way, and there is another electron which is denoted in this way. Now for this there is a convention. This has a spin of plus half and this has a spin of minus half. And if you actually talk about the electron, what you will see is, the electron is somehow, this is spherical. This is actually trying to revolve. This is actually revolving. This is revolving in this manner. This is revolving round and round. So what you can see here is either it can go this way or it can go this way. Either it can go clockwise or anti-clockwise. So what we will see here is minus half stands for anti-clockwise and plus half stands for clockwise spin. This is the basic concept of spin quantum number. I hope all this is clear to you. If you could understand this clearly, please show this with a like or with a comment, whatever suits you, and let's move forward. Now let's talk about the periodic table. Now let's talk about the position of sodium in the periodic table. Let's quickly bring a periodic table here. Yes, here is our periodic table. Yes, I took this from PubChem. Now let's talk about the position of sodium here. Okay, well, if I talk about sodium or Na11, I'll write the electronic configuration now because I know the quantum numbers now. See, the quantum numbers are N, L, Ml and S. So based on this, let's write the electronic configuration. What we'll know from here is 281. There were 3 shells. N is equal to 1, N is equal to 2 and N is equal to 3. This is how you used to do it in the 9th class. Now moving ahead, we see that in the first shell, what you find is 1s is the only possible orbital here. For n is equal to 2, you see that 2s is possible and 2p is possible. For n is equal to 3, 3s is possible, 3p is possible, 3d is possible. All these are possible, but do we need so many? No. You'll simply fill the electrons now. You have these rooms ready. Now you have to fill the electrons. S can accommodate a maximum of 2 electrons. This one also 2. P can accommodate a maximum of 6 electrons. And finally, if you see here, 10 electrons are already filled. You just have to fill 1 more electron. So this is how you got this electronic configuration very simply. So it is 1s2, 2s2, 2p6, 3s1. And this is the electronic configuration of neon. So you might have found that many books have this thing represented like Ne3s1. So basically this is the nearest noble gas. That is, in this case, it is neon with an atomic number of 10. So this is how we actually write electronic configuration. For atoms, of course. Now it's very simple to write it for ions as well. If I talk about Na plus, how will you write it? You will simply write 1s2, 2s2, 2p6. Okay. Now this is the exact similar electronic configuration as a noble gas. And this is how you see that in the valence shell, that is in the second shell, you see that there are 8 electrons filled, and this is the octet rule. This is how you see that the octet is complete in case of Na plus ion. That's why sodium takes the pain to lose an electron and form Na plus, because of this stable octet. Because of getting this octet configuration in the valence shell, it undergoes the process of losing an electron. And this is how they are seeking stability through attaining octet. Or you can simply say that it is attaining the nearest noble gas configuration for stability again. So as you can see here in the periodic table, how can we predict the position of sodium? As I told you, see, what you have to do is, for sodium atom, The valence shell is this one, that is 3s1. From here you will get the information. If you see the value of n here, the value of n here is 3. This gives you the period number. This gives you the period number. So you can simply say that this belongs to third period of the periodic table. And now what you see here is there is one electron here, and this will denote the group number. This will denote the group number. Now if you come here and if you find sodium in the third period as well as in the first group, it is verified. So this is how we do it. This is how we do it for S block elements. As you can see here, this is for S block elements. There are groups 1 to 2. So first and second groups belong to S block. Groups 3 to 12, all these groups belong to D block. Now there are 6 groups, that is from group 13 to group 18. This belongs to P block. And in this D block, there was lanthanum and there was actinium. So lanthanum and actinium, they open into a tunnel, and this tunnel consists of 14 elements each, and this is the F block or the inner transition series. So we won't be talking about the F block here or the D block in detail. Mainly we'll be concerned about some S block elements, and yes, some D block elements which are present as in trace quantities, but majority of the elements which we'll be talking about belong to the P block, and mainly our person of choice, that is carbon. As you can see here, carbon as well as nitrogen, oxygen, fluorine, chlorine. Then if you say sodium, potassium, hydrogen, all these are found in abundance in biological systems. Because we are talking about biology here, we are not going to chemistry here specifically. We are not going to chemistry. We'll be diverting here. We'll be moving to biology and biochemistry specifically. So we'll be talking about carbon, nitrogen, we'll be talking about oxygen, fluorine, we'll be talking about chlorine, we'll be talking about hydrogen, and also about certain elements like sodium, potassium. We'll be talking about certain elements like zinc, copper. We'll be talking about iron, cobalt, nickel. These are important to us, not all. Not all the elements are important for biological systems. So this was something important. And yes, for S block elements, if you see the value of n, this gives you the period number. And if you see in the electronic configuration S1, this number gives you the group number. For P block, it will be slightly different. For P block, what will happen is, generally, if I take an example of carbon, for carbon, that is with atomic number 6, it is 1s2, 2s2, 2p2. What you see here is, this is n is equal to 2. Total electrons is 4, but you have to add 10 here because there were 10 groups in between. There were 10 groups in between. So you have to add 10 here. So 4 plus 10 gives you 14. So yes, carbon belongs to group 14, and the period here is 2 because period is simply denoted by L, valence shell. So the period here is 2 and the group here is 14. This is how you find elements in the periodic table. This is how you actually denote their positions in the periodic table. Now, talking about carbon. Carbon is very important. Carbon with atomic number 6. Why? Because carbon is very versatile. And what is the reason behind this versatility? The reason behind this versatility is, number one, tetravalency, and number two is catenation. Two very important properties shown by carbon. Now, tetravalency means a valency of 4. But if you look at the electronic configuration now, that is 1s2, 2s2, 2p2. If you draw the box orbital diagrams, 1s, 2, 2s, 2, 2p, 2. Now you see that actually there are 2 unpaired electrons, so it will be able to form only 2 covalent bonds. It won't be able to form 4 covalent bonds with this. Now here comes an important concept. This is carbon in its ground state. We'll take it to its excited state. But talking about that later, let's talk about catenation first. What is catenation? The property of self-linkage. This is the property of self-linkage, due to which carbon can form chains, it can form rings, and it can form thousands of different compounds, which you see in nature. So let's talk about the excited state of carbon. And we'll talk about covalent bonds as well. See, what happens is carbon in its ground state, as we just saw, 1s, 2s, 2p. Here we have 2 electrons, 2 electrons here, 2 electrons here. Now, what carbon will do is it will try to enter an excited state. In this excited state, what will happen is it will try to send this particular electron to this empty orbital here, to this empty 2p orbital here. And this electron will go from here to here, and therefore this will become unpaired as well. And here will be another unpaired electron. So there will be 4 unpaired electrons now in the excited state. So here, if you see, there will be 4 unpaired electrons here, like this. So these are the 4 electrons, and now carbon will actually be able to show its tetravalent nature. What will happen here is all these orbitals will undergo mixing. The old homes will be broken and new homes will be created. And these homes will be equal in energy. These will be degenerate in nature. And this is a concept of mixing of orbitals. And this concept is known as hybridization. So hybridization will take place, and this hybridization will lead to formation of 4 such orbitals. Now, did you notice there was one s orbital? I mean, there was, I can write it in this way, one s orbital and 3 p orbitals. So what you can say is the hybridization is of sp3 type. Very simple. 1s and 3p. So what you are getting is each of these orbitals. Now each of these orbitals is neither purely s nor p. It is actually sp3. So this is sp3, 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 sp3. All these orbitals are of sp3 type, and this is how it is formed. What we can say here is, what if there was another case? What if only 3 of these orbitals went under hybridization and 1 was left behind? What if 1 p orbital was left behind, unhybridized? So in this case, what would happen is another type of hybridization would take place. That is 1s and 2p. And there would be 1p that is unhybridized. This type of hybridization would be called as sp2 hybridization. This would be called as sp2 hybridization. And this unhybridized p orbital would remain as it is. There would be another one coming close to it, and it would form sideways overlap. We'll talk about it just now. So I hope you have understood this. That is, 4 sp3 hybrid orbitals will be formed here. If I talk about sp2 hybridization, there will be, so this is total 4. So 1s and 3p forming total of 4 such orbitals. 1s and 2p forming total 3 such orbitals. And there will be one more case. There can be one more case possible. That is, 1s is there and just 1p is there. In this case, the hybridization will be sp hybridization, and there will be only 2 such orbitals being formed. And what would happen here is 2 p orbitals would remain unhybridized, and these would again form sideways overlap like this, and like this. So this is how it would form overlap in sideways configuration. But what about our hybrid orbitals? Hybrid orbitals would actually come closer. As you can see, I can draw a hybrid orbital here. See, s was initially spherical, p was dumbbell. Now both hybridized to form an orbital like this, which had characteristics of p as well as s, but neither purely s nor purely p. So this is an example of sp3 hybrid orbital. And as you can see here, if we compare sp3, sp2, sp, the percentage s character keeps on increasing as we move from sp3 to sp2 to sp, right? The percentage of s increases because relatively p is less in comparison to s. So the ratio, basically we talk about the relative ratio here, if you talk about the percentage s character. Now sp3 hybrid orbitals, there are 4 such orbitals, and how to arrange 4 such orbitals in space? What we see is the best shape, the best structure to arrange this is in the form of a tetrahedron. In the form of a tetrahedron. If you talk about a tetrahedron, basically from the center, like this is coming out of the plane, this is going into the plane, this is on the plane. Now, if you actually try to draw the triangular faces, this is one face, this is one triangular face, this is one triangular face, and this is one triangular face. So there are 4 triangular faces or hedra possible, like this, this, and this one. So what happens is, if you talk about these sp3 hybrid orbitals, these will be arranged around this carbon in this manner, like this. This is how it will be arranged, and this is sp3 hybrid orbital. All these are sp3 hybrid orbitals. What happens is, if hydrogen comes with its s orbital, again it doesn't undergo hybridization because it has one s orbital only. So if hydrogen comes here with 1 electron and carbon has its electron, hydrogen has its electron, and this leads to the formation of a covalent bond. This covalent bond, which is formed due to head-on overlap, this type of bonds are called as sigma bonds. These are all strong bonds formed between carbon, hydrogen, similarly CH, 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 and this is basically CH4 or methane. And you can see 4 sigma bonds being formed here. And if you talk about carbon, now here the hybridization is of sp2 types. This is of sp2 type. So what happened is, this is how the 3 sp2 orbitals were arranged. Here came hydrogens again. Now, the important thing here, thing to note here is the unhybridized p orbitals. These p orbitals, which I've shown in red, these are unhybridized. And these unhybridized p orbitals also have electrons, and they can undergo sideways overlap. This is how they will form sideways overlap, and this will eventually end up being like this. This is the formation of pi bond. This is pi bond, and pi bonds are weak in nature. So if you talk about, this is an alkene, that is ethene. Similarly for ethyne, there will be 2 pi bonds and 1 sigma bond. So the one default bond that is there, that is always sigma. If there are multiple bonds on top of that, the additional bonds are pi. So this is how we can show sigma bonds and pi bonds. So this is the sigma bond. So these are the sigma bonds and pi bonds present in alkenes and alkynes. So this was an example of alkene. This is an alkyne. This, as you can see here, is an alkane. This is how covalent bonds are formed, and I talked about various covalent bonds, that is sigma bond and pi bond. Now let's move ahead. We understood the concept of sigma bond and pi bond. Let's end with the concept of electrovalent ionic bond and a basic fundamental concept, that bond formation and bond breaking. What is the energetics behind it? So talking about electrovalent bond or ionic bond. See, what are ionic bonds? If I talk about sodium ion and chloride ion, there is Na plus, there is Cl minus, and there will be certain electrostatic forces of interaction. There will be electrostatic forces of interaction. Why interaction? Why not only attraction? Because there can be some repulsion involved as well. If you talk about an atom, it has nucleus, there is another atom. Yes. Now there will be electron here. This will have its own electron. There will be positive charge here, positive charge here. Now this positive charge will repel this one. This will repel this one. This will be repelling. This will be repelling. Again, there will be some attraction involved as well. This electron will be attracted to this nucleus. This will be attracted to this one, and vice versa. So there are multiple types of interactions involved. So that is why we generally call these things as interactions, not always bonds. All interactions can be called as, all bonds can be called as interactions, but not all interactions can be termed as bonds because of their strength. Not all interactions are strong enough to form bonds. So now, talking about Na plus, Cl minus. Na plus and Cl minus, they have strong Coulombic forces of attraction. Strong Coulombic forces of attraction. So what happens is, if there is a positive charge of plus Q, there is a negative charge having a charge of -1. So there is a positive charge, negative charge. Both have the magnitude of the charge as Q, and there is this R distance that is separating them. What you can write here is the force between them will be equal to K Q1 Q2 upon R square. And this is the most important thing. that F is inversely proportional to the square of distance separating these two charges. So this is called as inverse square law. Force is inversely proportional to the square of the distance separating these two charges. So this is the electrostatic force of attraction. Now this K can be expanded in this way. The electrostatic force is equal to 1 by 4 pi epsilon. Now this epsilon stands for dielectric constant. 1 by 4 pi epsilon Q1 Q2 by R square. For biological systems, we talk about epsilon. If we talk about ideal systems, for example, vacuum, for vacuum, we will be talking about epsilon naught, that is the permittivity of free space, but we won't be talking about it here. We'll be talking about dielectric constant here because obviously in case of biological systems, there will be medium involved, and in most of the cases, the best universal solvent will be involved, that is water. Aqueous medium will be involved. Fine. So we'll be talking about dielectric constant here. So yes, we'll be discussing these interactions once more while we'll be talking about proteins and all. Whenever we'll be discussing about proteins and the weak interactions that are involved in the biomolecules, we'll again talk about these interactions and the strength, the order of magnitude of these interactions. As of now, we are understanding this from a chemistry point of view because obviously we are talking about the fundamentals of chemistry. So now what happens is, let me tell you about one important thing. If you are talking about aqueous medium, obviously there will be water, delta positive, delta negative, because it is polar. Water is a polar compound. The bonds, because of the electronegativity of oxygen, the bond is polarized. The HO bond is polarized, and oxygen has a delta negative charge, partial negative charge, and hydrogen has a partial positive charge. What happens is, this is how the water molecules are arranged. This is how the water molecules are arranged, and this is how every time there is an interaction being formed, there is some amount of energy being released. Every time there is an interaction being formed, for example here, H plus will be coming close to this, and similarly there will be thousands of such water molecules which will be surrounding this. Similarly here, on both sides they will be surrounding it, and they will be forming solvation spheres. This is called as solvation spheres, or specifically when the solvent is water, it is also called as hydration spheres. And this is the process of hydration that will go on. And this is how every time an interaction will be formed, this will release some amount of free energy. Some amount of energy is released every time. There is some amount of energy released, energy released. And finally, all this energy together will be responsible for breaking the bond between the strong force between Na plus and Cl minus is easily broken with this tremendous amount of energy released by the formation of simple, small interactions between water and these charged ions. And this is how solvation takes place. This is also the similar way in which hydrolysis takes place, and the net delta G, the net free energy change, is highly negative in this case. So this was all about electrovalent bond or ionic bond. Let's conclude this session with one important concept, one important rule of chemistry, that is bond formation. The process of bond formation involves release of heat. I can say release of heat or energy. And in case of bond breaking, if you talk about bond breaking, in this case, energy is actually required. So there is requirement of energy. Very important. So we'll talk about, as I told you, we are talking about heat. And as you know, that whenever we talk about heat exchange, we talk about enthalpy. And also we don't talk about absolute enthalpy. We talk about delta H, that is change in enthalpy. Whenever we talk about change in enthalpy, if you see that whenever we talk about any kind of change, say change or delta, this simply means final minus initial. Now, if you are adding heat to the system, if it is required by the system, you will be actually adding, you will be supplying heat to the system, and therefore delta H will be positive. And this is called endothermic. So bond breaking is an example of endothermic process. Here we are not talking about endergonic processes. Endergonic or exergonic processes are called so based on delta G, that is free energy. Here we are talking about enthalpy. Fine. So if there is release of heat, if there is release of energy, so this, the sign will be minus, and this process will be called as exothermic. So sorry, this will be called as exothermic process. And obviously in this case, for positive, the final will be greater than initial. For this case, final will be less than initial. That's why we are getting a negative value here and a positive value here. So this is a fundamental concept, that bond formation is related with release of heat. If there is bond breaking, there will be requirement of heat, and this is valid always. If there are exceptions, there will be something more to the picture which you are not seeing, but the fundamental concept will remain the same. So this is all for lecture 1, chemistry fundamentals part 1 in Biochemistry Decrypted. I hope you enjoyed learning in this whole session. Do let me know your feedback in the comments section. Thank you so much. Thank you so much for attending, everyone. We'll see you in the next lecture.